So in the last class we discussed sort of the ray paths and the resulting intermodal dispersion in step index fibers or waveguides. Today we'll see how graded index, using a graded index instead of a step index, can help reduce that intermodal dispersion by a lot. Okay. So, okay, so recall at the end of last class, we discussed that graded index means that in the core, the refractive index varies continuously, right, according to some smooth curve. It's not constant in the core, right? So this is some n of x if it's a slab waveguide, or n of r if it's a fiber, right? So again, let's call this z. Right, and basically, so last time we discussed that if we launch a ray at some angle to the axis, basically the path taken is now a curved path, not straight lines, right? Because the refractive index is continuously varying. Right, so now basically the core is an inhomogeneous medium, right? In case of the step index, the core is a homogeneous medium, right? Everywhere the refractive index is the same, but in graded index now the core becomes an inhomogeneous medium. Okay, so last time we discussed basically how this ray will get bent every time, right, as it goes away from the axis and eventually turn back, right? So we'll calculate the exact. So first we'll derive an equation which can describe the propagation of rays in a graded index medium, and then we'll specifically for some specific examples derive the exact ray paths, and then calculate like the time taken by the rays and accordingly the intermodal dispersion, right, and then compare to step index. So now, so imagine like a layer here which is at a distance x, right? A thin layer at a distance x, right? So if you look at that, so right, basically what we saw last time is basically the ray gets, so the lower layer has slightly larger refractive index than the higher layer, right? So this is, let's say, n of x, this is n of x plus delta x, which is slightly lower because the refractive index is going down. Right? So the ray gets bent away from the normal, and like that, right? So if the angles of incidence at each layer, if we define as some theta of x, right, then we know from Snell's law, right, that this relation holds, right? The refractive index times the angle of incidence is equal to the refractive index on the other side times the sine of the, and that angle of refraction is now again the angle of incidence for the next layer, and so on, right? So this holds for, again, I can do it at the next layer, next layer, next layer, next layer, right? So basically, what it means is that for any x, this quantity is a constant, right? So I can change x, but n at that place times the sine of this angle with respect to the vertical will be a constant, irrespective of where I am. Right, so now if we just do like a, so we know that this angle is 90 degree. So then this theta, which the angle that it makes with the vertical, the angle that it makes with the horizontal axis, so if we call that phi, right? So that is 90 minus, so phi angle made with the horizontal axis, the propagation axis, is 90 minus theta at any x again, right? So basically I can write this as cosine of theta, or sorry, cosine of phi x, right? Because so basically we I guess want to express in terms of the angle made with respect to the propagation axis, right? So like this angle, or at any point the angle made with the horizontal. Okay, so this quantity is a constant. So the refractive index, if you go to any transverse coordinate away from the axis, the refractive index at that point times the cosine of the angle that the ray makes with the propagation axis, that is a constant. Okay, so we sort of denote this constant by this beta tilde. Okay, so this beta usually denotes a propagation constant, something like the k vector. Okay, we'll see that more explicitly when we actually solve the wave equation and do the rigorous wave analysis and solve for modes. But here, sort of, you can see that, so this is n times cosine phi x, right? So if I multiply by 2 pi by lambda, or k naught, which is the wave vector in free space, then this will be something like k times n will be the k vector in the medium, and then cosine phi means like that's in the direction of propagation, right? So that's something like a propagation constant in the direction of propagation, right? So that's usually denoted by the quantity beta. So here in this case we call this beta tilde because it's something like that, but not exactly. Okay, and so basically different rays. So you can see that this is a constant, right? So x equal to 0 is the axis, middle of the waveguide. So basically n at x equal to 0, which is the middle, times the cosine of this launch angle for the ray, right? So we call that theta I. So initial launch angle. So cosine of theta I, this is basically beta, right? So if I change this angle of the launch angle of the ray, so if I launch a ray at a slightly different angle, right? So that corresponds to a different beta, right? So basically, for different betas, we'll get different rays. Okay, so this is an invariant along the ray path. Okay, so now let's take a small portion of this ray path, right? So probably do something like that, right? So let's call the distance it travels ds. So in the z direction it's dz, and in the x direction it's dx. So this is at a distance x from the, so this makes an angle theta x in the horizontal, right? So we can write ds square as, right? So if this is a small enough length, then this can be approximated by a triangle, right? So this is close to a straight line if this is very small. So then we can use the Pythagorean relation, right? And then we also know that this cosine theta here is basically dz over ds, right? Or equivalently, we can write ds over dz as 1 over cosine theta at x, and from here, what? Sorry, I'm keep switching between phi and theta. I guess. So here we called theta as the angle with the vertical and phi as the angle with the horizontal, right? So maybe I'll switch to phi here. Okay. And from here now, you can see that cosine phi is basically beta over n. So you can write this as okay. So ds by dz, you can use this. So basically, if we divide this equation by dz square, so then we get ds right, and for ds by dz we plug this in. So we basically get, okay, so what kind of equation are we looking for, right? So what is happening, the ray as it propagates along z, the x coordinate is changing, right? So this curve is basically some function x of z, right? So as z changes, how is the x coordinate changing? So we are looking for some equation x of z. Right, so basically we want a differential equation in terms of x and z, fine. Right, so again we substitute ds by dz equal to that, so we can get now an equation, okay, what we want, like an equation of x and z. Okay, so from here, first thing to notice is that, so the left hand side is a positive quantity because it's square. So which means the right, to get real solutions or like actual ray paths, the right hand side also has to be positive, which means you can from see here that beta tilde has to be less than right. So if I choose a particular beta, right, then the ray path exists only in the region where the refractive index is more than this beta, right? So the ray will only exist, so here in this case, like it's existing in this region, right? So this, in this extent, basically this n of x, so if I mark beta on this scale, so beta tilde will be somewhere here, and in this region, the refractive index is always greater than this beta, right? So as I am changing the launch angle, I am changing this beta, I am changing the extent over which the ray will go. Right, and we can also see where the turning point will be, right? So if this is some x of t where the turns back, so that will occur at when n at that point is equal to this beta, right? Because beyond that the refractive index will become less, and so the ray can't go there. So given a refractive index profile, right, and then given an angle at which we launch the ray, we can find out where the turning point will be. Right, and now from this relation, you can also see that for the turning point, so for x equal to xt, cosine phi at xt is 1, right? Which means phi of xt. So at the turning point, the ray is tangential, right? So this is 0. So the angle made with the horizontal at the turning point is 0 because that's where it's turning back, right? That also you can see. Okay, so this is basically like the ray equation, right? From solving which we can get this x of z, the exact ray path. But we can simplify that equation a little bit more. So basically, if we differentiate this once more with respect to z, right? So we get on the left hand side we get that. On the right hand side, this beta is a constant. Right, so then dx by dz gets cancelled from both sides. And we end up with a second order differential equation here. Okay, so this is known as the Ray equation. Or sometimes the iconal equation. Right, so basically solving this, given a refractive index profile, we can find out what x of z, the path for the ray will be for a given launch angle or given beta. Okay, so we will first straight away check for the simple case. Let's for the step index, right? So for the step index, n of x is a constant. Right, which means this derivative is 0. So step index. Right, so second derivative of x with respect to z is 0. So solution is straightforward, right? X is some constant plus another constant times z. Right, so you can see this is straight line, right? And we already sort of knew or we discussed that in the step index, obviously there will be straight lines. So a and yeah.
Sir, the inequality for the extent of ray path.
Yeah.
I can have beta tilde is equal to n of x. That corresponds to phi equal to 0. It's along that.
Yeah, so that's the turning point. Okay.
That is when the ray is along the fiber axis.
Yeah. So to be more precise, I should put them equal to that. You're right. Yeah. So what you were saying is that if I launch with launch angle 0, so theta is 0 along the axis. So in that case, beta tilde will actually just be this n at 0, right? And in that case, the path is just a straight line, like we had for the step index. This goes. Right, so okay, so that's satisfying that we can recover the solutions that we expect for the step index, right? But of course, we are interested more in now some other kind of refractive index profile, right? So the most popular after the step index is what is known as the square law medium, where basically this n square is a square or parabolic function, right? So it's also sometimes referred to as parabolic index, but this name is slightly confusing in the sense that, so what we actually mean is that the square of the refractive index varies quadratically. Okay. So although it's called parabolic index, it doesn't mean that the refractive index is varying parabolically. It actually means that the square of the refractive index, or the equivalently the dielectric constant, has a quadratic dependence. So inside the core, it has this dependence, right? So so beyond x equal to a, it becomes constant, which we call n2 square here. Right, so inside the core it varies quadratically. Right, so this is like a parabola. And then into the cladding it's constant. Right, so at x equal to 0, this is n1 here. And then in the cladding it's n2. Okay, so this delta we discussed is sort of like the normalized refractive index difference. So from here you can see that delta here is n1 square minus n2 square divided by n1 square, or 2. So in the last class we had denoted delta as something else, right? Like we said something like this. So this is either n1 or n2. So this looks slightly different, but if n1 and n2 are quite close, right? So these two expressions are actually very similar, because so this I can write as n1 minus n2, n1 plus n2, right? And then n1 plus n2, if n1 and n2 are very close, I can approximate as 2n1. Okay, so that cancels out the denominator, so this roughly becomes n1 minus n2 by n1. Okay. Anyway, so basically for this, we want to solve this equation for this this kind of medium, right? So again, what kind of paths we can have? Right. So one limit, as one student said here, is if I launch the ray along the propagation axis, right? So then that we expect to go just straight through, right? So this will be if beta is equal to n1, right? If this beta tilde value is n1, then that means it's a ray along the, right? So now if I launch something that goes up to the edge and comes back, right? Which means the turning point is where n becomes equal to n2, right? And from here you can see turning point is that the n becomes equal to beta. So basically this ray would correspond to beta tilde being equal to n2. Right, so these are the two extremes. And any value between n1 and n2, you'll have ray paths going like that, right? So for any angle here, theta I, such that n1 cosine theta I, which is equal to beta, lies between n1 and n2. I could also launch a ray at even a steeper angle here, right, such that this beta is greater, or sorry, is less than N2. Basically, in that case, that ray will not get totally internally refracted and it will just leak out of the meter. Okay, so again, from there, the guided rays happen for this beta theta between N1 and N2. Right, so basically, we just need to plug in this expression for n square of x into here, right? So you can see that n square of x has an x square, which means so when we take the derivative with x, we'll get a linear function of x. So if you just go ahead and do that, the equation that we get is that where this constant gamma I can write like that. Okay. So very simple equation. Just you can check. So I mean this equation you've seen many places before, right? What are the solutions? Sines and cosines. Right? So, that will be the general solution. Right? So which means this path here is actually a sinusoidal curve. Right? And if I change beta, which is basically changing the launch angle, then that is changing the period, right, of this sinusoid. Okay, so I mean, let's consider the rays starting on axis, right? Which means what? That so x at z equal to 0 is 0. Right? Rays starting here at the origin, so this is z equal to 0. So from there, you immediately get this b has to be 0. Right, so then the rays take an even simpler form, just sine. Right, so these are different sine waves. Okay, so what is this period here, right? So the ray path repeats itself after period zp, right? So that period zp is basically 2 pi over gamma, right? So from here, right? So again, the period depends on this beta, the launch angle, and it's also depending on the refractive indices and the size of the photon. So typically, like for example, in fibers, N1 and N2 are very, very close, right? Which means basically you can see that the angles, this angle will be very small, right? Because so beta prime is N1 cosine theta I, right? That has to be greater than N2, but N2 is almost equal to N1, just a little bit smaller, right? Which means cosine theta I is almost 1. right? Which means theta I is close to 0. So most of, like all the rays, guided rays, are almost hugging the axis, right? So, right. So for this delta being very small, which is usually the case, basically beta tilde is almost n1, right? Because again, this cosine theta I is almost 1. So then you can see that this period becomes independent of this n1 or beta. Right, so in this limit, all the rays have the same period. It doesn't depend on beta, right? In the limit when n1 is almost equal to n2, all the rays are sort of making a very small angle and hugging the axis. In that case, all the rays almost have the same period. Right, so they look something like okay. So of course this is slightly exaggerated, right? So they can have different angles, but all the angles are very, very small and the period is almost the same. Right? So in that case the rays look like that. Right, so to get the complete solution, we still need to figure out this constant capital A, right? So that we can get from this launch angle again, right? So this initial angle theta I, right? That's the slope dx by dz at the initial z equals 0. That's this angle. So we can find the derivative dx by dz from here and put z equal to 0. So this is just a times gamma. So from here we can get a. So we use the value for the expression for gamma. Right, and then beta also now we can put n1 times cosine theta I, right, by definition. So from here we get this A as that. Okay, so this constant A, which is sort of the amplitude of the wave, right, just depends on the launch angle theta. Right. And again, I can write it instead of theta, I can write in terms of beta tilde. So I can also write it like that.
Excuse me, sir.
Yeah.
Sir, what is theta 1?
Theta 1 or theta I. Right. That's the initial launch angle of the ray. Right. So as I change theta I, I'm changing this beta tilde. Right. And for each beta tilde, I get a different rate. Right. That's why this tan of theta I is the slope at z equal to 0. So the initial launch angle. Right. So as I change theta I, I'm varying beta tilde. So if theta I is 0, then beta tilde is equal to n1. That's really like that. Right. As I increase theta I, beta tilde goes down because beta tilde is, as we saw, n times cosine theta. Right. So n1 times cosine theta I. That's less than n1. So as I keep increasing this, beta tilde keeps going down. At some point, it becomes equal to n2, and that would be the ray corresponding, which will go up to the edge of the cladding and come. Right? And if I further increase the launch angle, then beta becomes less than n2, and then those rays will not be carried till escape. Right? So basically, the only degree of freedom here is basically the initial launch angle, right? Which determines this, the amplitude of the ray. Right? All the others are just constants of the medium. Okay, so yeah, so we have the complete solution then, right? We can write x of z in terms of the parameters of the medium and the 1 degree of freedom that is the initial launch angle. Okay. So hopefully that's clear, like the ray paths. So this is the general ray equation for general medium. Then specifically for a square law medium, we saw that the rays would follow sinusoidal paths, right? Where the period is sort of determined by the launch angle. If the index difference is very small, then it just depends on the pore size and the index difference. Right? And right, so now we have expression for the ray paths, right? And again, what we are interested in is, like for optical communication, for example, let's say we are sending pulses here, right? So we want to see how much they end up broadening. Right, because again we launch light here, they couple to different rays, and if different rays take different times to arrive here, then the pulse would broaden, right? That's intermodal dispersion. So we want to see what is the intermodal dispersion for this kind of graded index medium, right? So then for that we need to calculate the time that these rays take, right? So again, for the step index, because it was straight lines and the core had a constant index, so we knew the speed, right? So it was straightforward to calculate. But here, because the refractive index is now varying continuously, the speed is also varying continuously, right? So let's see how we can calculate like the transit time for different rays in a graded index medium. Any questions on the ray paths themselves? Okay, so yeah, so we want to calculate the transit time for the different rays, or like let's take a general graded index medium again with some n of x, and so that will correspond to some ray paths. And we want to calculate for any single ray path, how do we calculate the time it takes? Right, so again, we take a small portion of the path. This is ds. This is the angle phi x. So the time that it takes to cover this small distance ds, right? So let's call that d tau. Will be just the distance ds divided by the velocity at x, right? So the velocity is basically c over n, right? So this will be the refractive index at the coordinate x. Okay. And so we see that basically the ray paths are periodic functions, right? So they repeat after some period. Okay. So let's calculate. So let's say the time taken to cover one period. Let's call that tau p, right? So the time taken to go from here to here, right? Cover a distance zp in the z direction. So that will, I just integrate tau, d tau, right, over one period, or like delta z equal to zp, right? Integrate z over the distance zp. Right, so again we can write this ds in terms of x and z. So this ds, again this dx square plus square root. I write that as take dx outside, right? Because n is a function of x. So, like for example, if I get an integral in terms of x, right? So I take dx out, and then recall we had expressions for dx or dz from the ray equation already. So for this, right, we had this equation. So we can plug that in here. Okay, so from here you can see that 1 plus dz by dx square will be equal to that. Right, so this we plug in here. Right, so again, if you look at the ray path, so it starts from x equal to 0 and then goes to some x equal to xt, the turning point, right, and then sort of comes back and then repeats. Right, so we can divide the period into 4 sort of equivalent sections, like each of which have the same length and take the same time, right? So this is the same as this in terms of length and also speeds because it takes the same, it accesses the same x coordinates, right? Just a mirror image. Similarly, this that flipped here, right? So all these 4 quarter periods take the same time. Right? So let's call that, so if the time it takes to complete a period is tau p, then it's tau p by 4, right? For each of them. And so what is tau p by 4? It's this integral evaluated from 0, x equal to 0 to x equal to x, right? So tau p by 4. Right, of this expression here. Okay. So if we know the refractive index profile n of x, we can evaluate this integral, right? For a given beta tilde or a given launch angle. So for that particular array, this will be the time taken to cover a quarter period, right? From which we can reduce the entire time, right? Because it just repeats. And xt is basically, again, recall that, right? Given by this condition. Right, so in general, we can evaluate this for any kind of medium. So let's again look at the square law medium and see what we'll get for that case. Right, so if you have a total length L of the waveguide or fiber, then the total time taken to cover the whole length L, I can just calculate like that, right? So to cover Zp it takes tau p, so per unit length it takes that much amount of time, so multiply by L. So tau p we can calculate from this integral. Once we have tau p, and Zp, remember, also we know from solving the Ray equation. So we know in terms of the parameters of the medium. So once we evaluate this integral, we know tau p, we know already Zp. So but using this expression, so for a given length L, we can find what is the transit time. So again, consider square law medium. Right, so to evaluate this integral, first thing to calculate is the turning point. Okay. So to calculate the turning point, basically we use this relation. Right, so the first for the square law medium, right, we put x equal to xt here and put it equal to beta there, right? So from here we get xt, the turning point for a given beta. Like that. Right. So yeah, so we just evaluate this integral. So for n square of x, you put the parabolic profile. right, over dx. Right, so to simplify this integral, what we can do here is add and subtract beta tilde square in the numerator, right? Because we have this expression minus beta tilde square in the denominator. So if we add and subtract this beta tilde square, right? So the first term, this minus beta tilde square, we can cancel out a factor there, right? And the second term will just be a constant, right? So if we do that, we can reduce the integral to standard integrals that we know the expressions for. Right, so these are standard integrals now. Square root of some constant minus x square, here dx divided by square root of some constant minus x square. So these are standard integrals that we know the analytical expressions for. You can look them up in any table of integrals or anything. Or you might even remember them from your preparation for engineering exams. Right, so just evaluate those integrals. So we get an expression for this time taken to cover one period. Okay, in terms of the parameters of the medium, right? So n1 is the maximum index at the center. Beta tilde is for a particular ray determined by the launch angle, pore size, respective distance. Right, so it may not be possible to solve this integral analytically for any general graded index medium, right? But for the square law, turns out we can analytically solve the integrals and it similarly was for the case for the ray paths themselves, right? So that's why the square law medium is sort of like a example medium that we consider. Also, practically, it's sort of easier to make. So how do we make these graded index media? Is so you take the step index fiber to start with, and then you dope, right? So you dope with some ions, which changes the refractive index slightly. And if you can like control the doping profile, so you dope more ions towards the center and reduce the doping concentration, and you go away, you can get some kind of graded index, right? So you can imagine that controlling that very precisely is difficult, right? Because also when you bombard ions, they sort of diffuse away. Right? So, but the square law sort of can be done fairly well. Okay, so we have this expression for the period. So to calculate the total transit time, along with the time taken to cover one period, we also need this expression for the period, which we already derived, right, from the ray equation. So recall the period was, for the square law medium, it was 2 pi over this gamma, because the ray paths were sine gamma z, and that gamma dependent on the medium parameters like that. Right, so now using these expressions for tau p and zp, we can get the transit time for a total length L in terms of the medium parameters. Right, so if we just put these expressions, you get okay. So different rays correspond to different beta tildes here. Right, so that we can use the same analysis that we did for step index to find out the amount of broadening delta t here. Right, so we calculate a ray corresponding to the minimum time and then the ray corresponding to the maximum time, and then take the difference. Right? So again, so tau min of L, right, will be, so you can imagine that will be the ray which goes straight through. Right, so this will correspond to beta tilde equal to n1. So that will just be n1 L by c. Right, which we could have straight away calculated, right? So the ray which goes straight through has a speed c over n1 because it always only sees refractive index n1 and it covers the distance L. Now the maximum time is taken by the ray which sort of takes the maximum curved path, right? So here we can see that happens for beta tilde equal to n2. It goes up to the cladding edge and then down. Okay, so the amount of broadening is the difference. So basically, we can get this dispersion parameter. So the broadening per unit length. Like that. Okay, so we can simplify that expression a little bit to write it in terms of this delta quantity, which is the refractive index difference. So right, so you can write this expression like that. And now this is, approximately just delta, right? And if n2 is very close to n1, we can also just approximate it like that. Okay, so one thing to note here is that the dispersion scales as the square of this quantity delta, which is the normalized index difference. So recall for step index, the intermodal dispersion was proportional to delta. Right? So for step index, it was this expression, n1 over c times delta. Here for the square law medium, we get n1 over c times delta square by 2. Right? So this going from delta to delta square really helps. Why? Because delta is very small. Right? So for typical fibers, delta is much less than 1, typically 10 to the minus 2 or 10 to the minus 3. Right? So basically, you reduce the dispersion by a factor of delta. Right? So 2 orders of magnitude or something. So recall if you put the numbers, some typical numbers, right? So you take n1 1.46, delta 0.01. Right, so for the step index, it was about 50 nanosecond per kilometer. Right, whereas if you put in the number here, you get about 250 picosecond per kilometer, or equivalently 0.25 nanosecond per kilometer. Right, so we've gone from 50 to 0.25. Right, that's like more than 2 orders of magnitude improvement. So equivalently, I can increase my bit rate, data rate by 2 orders of magnitude for the same length. So recall that we actually did this analysis for a slab waveguide, right? We took this coordinate as x, whereas for a fiber, you have to take the radial coordinate, right? And you can imagine that the equations that we need to solve, instead of the Cartesian coordinates, we have to actually use cylindrical coordinates, right? Which will be more complicated, right? So that's why we didn't sort of discuss that. We should just discuss the slab waveguide, but sort of miraculously it turns out that the final result is the same, right? So this dispersion, even if you take cylindrical coordinates and solve, you get the same. Okay, so this is true even for a fiber in cylindrical geometry. There is some discussion on that in the textbook. I've given the relevant reading. If people are interested, you can try to look at the complete map in the radial coordinate also. So that's much more involved. The basic ideas you can get from this Cartesian coordinate. That's why. Okay, so that's great, right? So instead of just having a constant, if you just grade the index, we can reduce the dispersion a lot, right? And so there is a question: can you explain maximum time again? So is this not clear? This one, right? This is the the extremal rays are one which goes straight through, right? So we start with angle 0. Then as you increase angle, we sort of go like that, right? The period becomes smaller and smaller as I increase the angle. And the maximum angle I can do is the one which goes up to the edge and comes back. If I increase angle further, then I actually lose those rays, right? So we discussed this already. So that corresponds to the ray which has a turning point at the cladding interface corresponds to beta tilde equal to n. Right, so this is the one which is taking sort of the maximum path. Okay, so you can sort of also check from the expression we had. I erased, right? So there is an expression for tau of L in terms of beta. Okay, so that just turns out to be an increasing function from beta tilde equal to n to n. Or yeah. So That clear? Another question is, how can we find the appropriate refractive index profile? So, finally, sort of what you're interested in is this amount of broadening, right? So that you can measure directly, right? And sort of from the amount of broadening, you can try to back calculate what kind of refractive index profile you have. Okay. The other thing is actually what, as I said, how these fibers are made is you start with a big preform, right? So millimeter, centimeter sized. Sometimes they're like this big, right? You can see. So this would be some kind of. You start with some step index core, and then you sort of dope with ions. So I guess you can try to measure the refractive index profile in the preform, right? And then as this is being pulled, you basically assume that as it thins, the refractive index profile sort of remains the same. But yeah, so it's difficult to directly measure the refractive index profile in a fiber, right? In that small scale, to directly measure the n as a function of x. It's directly to measure that is sort of not really possible, but you can do indirect methods as I said. So you can measure the pulse dispersion, right? You can try to do that at different frequencies, etc., different wavelengths, and try to back calculate from the broadening you get, sort of try to estimate. Okay, and nowadays, especially for communication, like telecommunication, information communication applications, we don't really use multi-mode fibers anymore, right? We just use single mode fibers. So in that case, this becomes redundant, like ray paths and these kind of things become redundant. You just have a single mode, and the dispersion in that case is measured in a different way. So we'll discuss that in more detail later. So nowadays, multimode fibers are just used in applications where you want to collect more light from your. So you're testing some sample or measuring something, and you want to collect maximum light. You don't care about the temporal waveform. You don't care about pulse spreading, or you don't care when the light arrives. You just want to collect more light because you have very low signal, right? So, for example, some types of microscopy, some spectroscopy, imaging kind of applications where you just want to collect as much light as possible and then take that light onto some small detector, right? So that's where multimode fibers are. Or in some other kinds of applications, for example, like where you need a lot of power, you need a lot of laser power onto a small area, like for machining or laser cutting or something like that. That's where multimode fibers are used nowadays. So not in information communication applications, because as you can see, it's just very limiting.
Excuse me, sir.
Yeah.
So why is that beta corresponding to N2? Beta equal to N2 is corresponding to the maximum time that is being taken.
mean, so from here you can sort of see that it's taking the maximum, or it's traveling the maximum distance, at least, right? That's sort of clear from here, right? And it's a little bit more complicated because the speed is not like for the step index. We just took, okay, we said that the ray which takes the maximum, which travels the maximum distance, also takes the maximum time. Here it's not so straightforward, but especially for the case where n1 is close to n2, right? So this change is not much, right? So let's say delta is 0.01 or something. Right? You can see that the change in speed will not be much, right? From c by n1 to c by n2, that percentage change will be. So if delta is 0.01, it's like 1%, right? But the path length you can see here, right? So compared to this path length is much bigger, right? The change is much bigger than 1%, let's say. Right? So this sort of concept that the maximum distance ray will also take the maximum time also sort of approximately holds true in this case, right? Although the speed increases as you go away, it doesn't increase that much that it can completely compensate for the increase in distance. Okay, so I mean, you can also just plot. So the tau of L we got. So here you can see it's something like this. You can just plot this from beta equal to n2 to beta equal to n1. So it will just be a monotonic function. It will look like this. So this is tau max, this is tau min. So this is beta equal to n2 and this is beta equal to n1. Okay. Any other questions on the square law medium? So to discuss briefly sort of a general kind of refractive index profile, we can generalize the square law profile to a power law profile. Okay. So, right, in general, I could have a power law index profile. Right, so n square of x varies as to the same form, but now the power of x here is some q. Okay. Cladding. Okay, so q equal to 2 corresponds to the power law, to the square law. Right, so q equal to 2 is the square law medium. You can see if I put q, if q tends to infinity, then you can see so x is less than a. So if that is raised to some very high power tending to infinity, this term becomes 0. right? So then that is like a constant refractive index in the core. So this is like a step index. Right? And for any other power of q, it will be some other. So for q equal to 1, it will look like a triangular linear profile. So if I plot n square of x versus x for different q's, right? So x. So q equal to infinity is the step index, right? So maximum value here is n1. This minimum value here is n2. This is a. So this corresponds to q equal to infinity. So as I reduce q to finite values, this becomes curved like that. Right, so this is q equal to 2. Right, so this is q equal to 1, a linear or triangular profile. Right, and for values higher than 2, it looks like that. And as you keep increasing q, it will go towards the step index. Right, so for example, let's say this is q equal to 4 or something. Okay, so we can do the same kind of analysis. Take this power law profile, put it into this integral, and try to find the transit time. Right, but I mean the math is more complicated because the integrals are not easy. But again, there's a brief discussion on this in the textbook if you want to know more. But for our purposes, we'll just see that sort of you can calculate the dispersion for any value of q here, like this. The expression that you get looks similar to what we had for the square law profile, except the constants are different. So a and b are some constants, okay, which depends on q. So a right, so again q equal to 2 will be the power law, so square law medium. Okay, but for any general q, that is sort of the expression we end up with a and b given by those constants. Okay, so we can try to, what we can try to do is minimize this expression with respect to q. Right? So that will be, so what we are trying to do is varying this q and see which profile is optimum in terms of minimum dispersion. Right? So we can minimize this function with respect to q. So if you go ahead and do that, so you see that the minimum occurs at q equal to 2 minus 2 delta. Okay, and then if you put this q equal to 2 minus 2 delta into the expressions for a and b and here, you get so the minimum value of this dispersion you get. Okay, so for the square law for q equal to 2, we had this expression n1 delta square by 2c. If I now change q to 2 minus 2 delta, so remember this is a very small change, right? Because delta typically is very small, right? So 0.01, let's say. So this is Q equal to 1.98, right? An extremely small change, but that reduces my dispersion further. So here you see we gain a factor of 4. Okay. So for Q equal to 1.98 and then the same values for N1 1.46, delta 0.01, this value comes out to be about 62 picosecond per kilometer. Right, so further reduced. Right, so that's the optimum profile. The optimum refractive index profile, which gives me the minimum intermodal dispersion, is a power law with Q equal to 2 minus 2 delta. Okay, so typically for fibers that means a value just slightly lower than 2. Okay, so in practice, actually it's very difficult to control the profile so precisely. Okay, so that's why square law sort of is good enough, and you will try to follow that. Right, to get it to 1.98 instead of 2 is that kind of accuracy in terms of doping the fiber is very difficult to achieve. But if you could do that, you could further improve. So if you plot this dispersion delta tau over L as a function of Q, so I have the dispersion here in nanosecond per kilometer. X-axis is Q. Okay, so as Q increases to higher and higher values, I go towards step index. Right, so this direction is towards step index. N equal to the Q equal to 1 is a triangular profile. Right, 2 is square law, and the minimum of this occurs at just a value below 2 here, right? 2 minus 2 delta. So the curve looks something like this. Okay, so it falls sharply near 2. Right, so this dotted line here sort of is like this 50 nanosecond per kilometer. Okay, the minimum value here, so let's say that is at 1.98. So in nanosecond per kilometer, you can see that's like 0.06 or something. Okay, so basically around 2, it's like there's a sharp dip where it falls by, like, you can see 3 orders of magnitude or more. Right, so at 2 you are here, somewhere here like 0.25. Okay, so basically practically if you want to make, they sort of aim for something around 2, right? So you don't want to deviate too much from 2, right? Even if you go to like 2.2, 2.3, suddenly you are almost close to the step index value. Okay, so if we zoom into this area here, then it falls very sharp, like it changes very rapidly around there. So again, like 1.98 is sort of the minimum. So this again. Okay, so even just like a 0.1 change increases your dispersion by like 2 orders of magnitude. So if you can precisely have like control your doping profile very precisely, then you can really lower the dispersion load. Okay, so in the initial days, people were sort of working hard on this, but as I said, eventually we moved to sort of few mode and then single mode fibers, where all this analysis doesn't hold anymore anyway. It's just a single mode problem. But recently, sort of, people are again interested, at least maybe in few mode fibers, if not highly multimode fibers, and that's again with the view to sort of increase data rates, right? So, although we can get extremely high data rates now through optical fibers, more than terabit per second, but the internet traffic keeps increasing year on year, right? So, how to increase capacity further? People are thinking that now we can do spatial division multiplexing. So, we already do wavelength division multiplexing, so different wavelength channels carry data parallelly. So now instead of that, now we also do spatial division. So different spatial modes will also encode data. So let's say you have a 4-mode fiber, then you have 4 different spatial modes, which also encode information. So that's like 2 bits in addition, right? So you can boost data rates that way. But of course, sort of at the transmitter and receiver side, it becomes more complicated. How do you encode data onto the spatial mode? But that's again sort of recent interest. So maybe people will start looking at these graded index things again. Let's see. So, yeah, any questions? So with this, I think basically that finishes our sort of discussion of ray optics or geometrical optics, right? So from now on, we'll move on to the actual wave optics or the how actually light is described, right? So we'll solve the wave equations in such structures and see what kind of solutions we get. Right, we'll get different electric magnetic field profiles which sort of propagate without change, right? And we look at their properties and they are called modes, optical modes. So we look at, yeah. So from now on, basically, we'll be dealing only with the wave picture and not with rays or geometrical optics anymore. So first thing next class we'll do is so consider like a planar slab waveguide like this, right? So we'll start with step index again, and then solve the electromagnetic wave equation with boundary conditions, appropriate boundary conditions, and solve for optical modes. So-called TE and TM modes. So first we look at the modes of these slab waveguides, planar slab waveguides in Cartesian coordinates, and then we'll move on to cylindrical coordinates and solve the wave equation in cylindrical coordinates for a fiber. So the basic sort of concepts that we get from the slab waveguide will hold for the fibers, except that the exact solution and how the modes look, of course, will be different because the structure is different. Right? And we'll also solve for modes in some gradient index media, like for example, square law media and such media.